Hi kids, these notes are over 9.4 and 9.5. 9.4 is called Geometry's Most Elegant Theorem, Pythagorean Theorem. This will be a review for you. There is a part of the Pythagorean Theorem that will be new, and that is called the converse of the Pythagorean Theorem. Your essential question is, how can I use the Pythagorean Theorem to find missing side lengths of right triangles? You should already know how to do this, and use its converse to classify triangles by angles. So as most of you know, the Pythagorean theorem states that if a triangle is right, meaning it has a 90-degree angle, then a squared plus b squared equals c squared. The a, b, and c represent the side lengths of a right triangle. So let's suppose I've got a right triangle. Side C is the longest side of the right triangle. It is always across from the right angle. This side is also called the hypotenuse. A and B are the two legs. Generally, A is the shorter of the two legs and B is the longer of the two legs. The two legs meet to make the right angle. So what this is saying is, if I square A, if I make this length of A into a square, that's A units by A units, then that means that square is going to have an area of A squared. A times A is A squared. And then let's say that I square side B, the other leg. So I make a square with its length so that its other side is B units long. Then the area of that square is going to be B times B, which is B squared. And then I do the same thing with side C. I turn that into a square. That's side C's length by side C. Then its area is represented by C squared, which is just C times C. Then what this theorem is saying is that if I take this area in square A and this area in square B and I put them both inside this square C squared, they will fit inside that square perfectly. That's what this theorem is stating. And so what this does is it creates a relationship between the three side lengths of a right triangle. There are two ways that you can use the Pythagorean theorem. One way you're familiar with. If you know the lengths of 2 out of the 3 sides of a right triangle, then you can just plug those lengths into the appropriate A, B, or C, whichever 2 that you know, and then you can solve for the third side. Easy. The other way is probably new for you. The converse of anything is when you switch the hypothesis with the conclusion. So our Pythagorean theorem stated that if a triangle is a right triangle, then a squared plus b squared equals c squared. The converse is if a squared plus b squared equals c squared, then the triangle is right. This seems to make sense. So if we know the value of A, B, and C, and we plug it into the Pythagorean theorem, and a squared plus b squared actually equals c squared, then that means the triangle is right. This makes sense. But let's suppose that we plug in A, B, and C, and a squared plus b squared actually is less than c squared. Then that means the triangle is not right, and it is an obtuse triangle. A and B form an obtuse angle. The reverse of that, or the opposite of that, is also true. If a squared plus b squared is greater than c squared, then that means the triangle is an acute triangle. So the angle formed by A and B is less than 90 degrees. Please write these down and come up with some way to remember these. So these are kind of like tests you can use these tests right here to determine what type of triangle you have here, classifying by angles. Okay, so let's try a couple examples. The first one says find the perimeter of a rhombus with diagonals of 6 and 10. This is all we know. So we have to think back to rhombus. A rhombus is a quadrilateral where all of its sides are congruent. We also know that the diagonals bisect each other and they are not congruent. So it might look something like this. This is not drawn to scale, so we're not counting squares here. But all 4 sides are congruent. My diagonals bisect each other, which means these 2 halves are congruent and these 2 halves are congruent. And they also intersect at right angles. Oh, that's so important. And if you look at these by SSS, all 4 of these right triangles are congruent. So we can just really focus on one of them. So Pythagorean theorem and the converse both have to do with right triangles. Let's go ahead and look at what we know. The diagonals are 6 and 10. The shorter diagonal is 6. That means each of its halves equal 3. And the other diagonal, which has a length of 10, has been bisected into lengths of 5 and 5. So let's go ahead and focus on one of the triangles. Okay, let me switch colors here. Okay, in order for us to find the perimeter of the rhombus, we're going to need to find one of the side lengths, we'll call it x, and then just times it by 4 since all 4 sides are congruent. Okay, so let's take a look at this triangle right here. We know 2 of its sides, the 5 and the 3. These happen to be the A and the B. Let's call the 3A and the 5B X, the side of the rhombus we'll call C, because it's across from the right angle. So all we're going to do is use the Pythagorean theorem. We're going to write it down, a squared plus b squared equals c squared. So this is what you'll use when you need to find a third side of a triangle that you already know is right. We're going to plug in what we know. A is 3, B is 5, C, is X. You can call it C if you want, that's fine. Now we're going to simplify. 3 squared is 9, 5 squared is 25. Make sure you're actually squaring the number and not doubling it. That's a common mistake. 9 plus 25 is 34. Okay, at this step, as you guys are getting more used to, you are going to take the square root of both sides. Anytime you have your variable squared equals a number. So when we take the square root of x squared, we get x. The square root of 34, we will need to see if we can simplify that. So off to the side, we're going to do our little upside down division. A prime number that'll go into 34 is 2. It goes in 17 times. And 17 actually is prime. So since I have no pairs, then that means the square root of 34 is already simplified. So this is the length of one side of our right triangle. Now we need to go ahead and find the perimeter of our right triangle. So since all 4 sides are the same, we're going to do 4 times this amount, 4 times the square root of 34. Since 4 is outside of the square root symbol and 34 is inside, we leave it just like that. So the perimeter is 4 square root of 34 units. Okay, this next example says find the perimeter of the trapezoid. We've got this picture. Some things we know about the trapezoid. We know that it's isosceles because both legs are congruent. In order to find the perimeter, we would need to find the length of all of its sides. Well, we've got the length of 3 of its sides. We just need to find the length of this third side, which is made up of 2 of these lengths, whatever they are, and then this length right here. That length right there is between these 2 perpendicular dotted lines, which look like the heights. So I know, because they're perpendicular, that this length will also be 20 here. All we need to do now is figure out how long these other parts are, and then we'll have all the pieces we need to find the perimeter. So let's take a look at these end right triangles. They are going to be congruent. by SAS. The two legs appear to be congruent, which is good. And we know, it looks like we know the side length of side C, which is 10. So let's focus in on one of these right triangles. Maybe this guy. Okay, in this case, usually with using Pythagorean theorem, you need to know two of the three sides in order to find the third side. There is an exception when the two legs have the same length as they do here. You can use the same variable for both of them, which will not introduce a second variable into your equation, and you will be able to solve for that. So let's call these two legs both x. I hope you can see this yellow. Actually, let me switch colors. Okay, so let's go ahead and label side C is the 10. It's across from our right angle. Our A and B are both x. So let's go ahead and see what happens when we put this into our Pythagorean theorem. We'll put x for A and for B because they have the same length. Our C is 10, so this is what we get. Now x squared plus x squared, those are like terms. We can combine those, and if you remember, there is an invisible 1 in front of both of those. So when we put those together, we get 2x squared on the left. The right is 10 squared, which is 100. Now all we have to do is solve for x. So we're going to get x squared by itself, like we've been doing, and then we'll take the square root of both sides. But the first thing we need to do to get x squared by itself is divide both sides by 2. So x squared equals 50. Now we'll go ahead and take the square root of both sides. The square root of x squared is x. The square root of 50, I'll go off to the side here. A prime number that'll go into 50 is 2. It goes 25 times. A prime number that'll go into 25 is 5. It goes 5 times. So I'm done. My last number is prime. We have a pair of 5s, which counts as 1 5. So the square root of 50 is equal to 5. And then the 2 that is not circled will stay inside. 5 squared of 2. This is the length of x, which is this part and this part on either side of the 20, that lower base. So now we've got all the pieces we need for our perimeter. Let's go ahead and add it all up. So our perimeter is going to be equal to, we've got the 10, the 20, and the 10 that we started with. That's 40. Plus we've got this 20 on the bottom. Plus we've got 2 of these x's, which are both 5 squared of 2. So we've got 5 squared of 2 plus another 5 squared of 2. Or you could do 2 times 5 squared of 2. That will give you the same answer. Now we're just going to combine our like terms. The 40 and 20 we can add to make 60. The 5 squared of 2 and the 5 squared of 2, because they have the same number in the square root part, the 2, we can add them together. They're considered like radicals. And remember, when we add like radicals, we're just adding the coefficients in front. So we're just adding these 5's together, which is going to make 10, but we're still going to have square root of 2. So the perimeter of this trapezoid is 60 plus 10 square root of 2 units. Okay, last example. Let's say we have a triangle, or we know the 3 side lengths of the triangle, in this case 2, 4, and 9, but we want to figure out what type of triangle it makes. Are all the angles acute? Do you have one right angle, or do you have one obtuse angle? Is it acute, right, or obtuse? So we're going to take a look at these 3 side lengths. The smallest number will always be your A, the middle size number will be your B, and the largest number will be your C. What we're going to do, we're going to plug these into A squared plus B squared and to C squared, and then we're going to try to compare how these two values, compare their quantities. Okay, so we're just going to plug in these numbers. A is 2, so we have 2 squared, plus B is 4, so plus 4 squared on the left. C is 9, so we have 9 squared on the right. We just need to simplify both of these expressions and then see, are they equal, less than, or greater than. 2 squared is 4, plus 4 squared is 16. 4 plus 16 is 20. We have 20 on the left. 9 squared is 81. So 20 compared to 81, 20 is less than 81. And if you look back to the converse of the Pythagorean theorem, less than meant that this triangle is obtuse. If it was a greater than symbol there, then it would be acute, and if it was equal, of course, it would be right. That's how you use the converse. Super simple. So these are the problems that you can practice for 9.4 if you'd like to, or you can wait until we do these in class. Have a good evening.